Hey everyone, in this video we're going to be talking all about systems of linear equations. So we're going to start with substitution and elimination, and so we'll be solving using those two methods, and we'll identify when a system is inconsistent, and we'll also be expressing the solution of a system of dependent equations, and then in the next video we'll be working on systems of three equations. Alright, so let's start with this example. A movie theater sells tickets for $8 each, with seniors receiving a discount of $1. One evening, the theater took in $4,000 in revenue. We're going to let X represent the number of tickets sold at $8. Y is going to represent the number of tickets sold at the discounted price, which was 8 minus the 1, so $7, and write an equation that relates these variables. So we can use 8 times X to represent for every X tickets, it's times $8 for the sale. Same thing with Y, being the number of senior or discounted tickets. They're $7 each, so 7 times Y. And then the total money brought in was $4,000, so what this means is here's our equation. So we have 8X, which is $8 times X tickets, plus 7Y, so $7 times Y tickets, equals the money that was brought in, $4,000. So this is just a quick example for how we can write an equation from an example like this situation. Now, if we had some more information, maybe about how many tickets were sold total, we can write two equations, and that would be a system of equations. So this is just an example for how we could get one equation. So here are some examples of systems of equations. And so if you take a look at example A, this is two equations and two variables, X and Y. And I like to label my equations because it's going to help us when we're solving these systems. And when we're solving, which is coming up in the very near future in the video, you're solving for the variables. So you'll be solving for what is X equal and what is Y equal. B is also a system of two equations. Again, the two variables happen to be X and Y. And the third one is a system of three equations, and you have three variables this time, X, Y, and Z. And so in that case, you'd be solving for what is X equal, what is Y equal, and what is Z equal that satisfies these three equations. Right here, for example D, this is a system of two equations, but three variables. So we only have two equations, but if you notice, there's three unknowns, X, Y, and Z. And then example E here is four equations and three variables, because if you look through the equations, there's X, there's Y, and there's Z. So these are just examples of the types of systems of equations that you might come across. So in this video, we're going to be focusing on systems of two equations containing two variables. For your linear equations, your systems, there's one of three possibilities for the outcomes. So there's only three outcomes that could ever happen when you're solving a system of linear equations. Possibility number one is that the system is considered consistent and your equations are independent. So consistent just means there's an answer. Okay, so consistent, there's a solution, at least one solution. Because if you notice over here, this is also consistent, and this one is actually an example where there's infinitely many solutions. So consistent means there's a solution to the system, and independent for this one means that there's two separate equations. When you graph them, it would be two separate lines. They're not the same, and they meet at one point. So graphically, this is some X comma Y. That's the answer, because you're looking for, when you're solving these systems, what is X equal, what is Y equal. So the answer would be X and Y, those two values, whatever those numbers are. Option 2 for your system of equations is that the answer is inconsistent, so there is no solution. So inconsistent means no solution. And that's because when you try to solve them or graph them, like let's say this is line 1 and this is line 2 from your equations, they're never going to intersect. There's no X and Y that works for either one of these equations, like together. So no solution. If you were to solve without graphing, you would get something that's just false. You would get something like maybe something like this, like this is never true. Okay, so inconsistent is a possibility, meaning that your system of equations just did not have a solution. And then the third and final possibility is that your system is consistent So it has at least one solution. This one actually has infinitely many solutions. Infinitely many solutions. And it's because the equations or lines were dependent. So when you graph them, this is actually both line 1 and line 2, equation 1 and equation 2. They're like laying on top of each other, and they meet at every single point. So every single x and y value here satisfies both equations. So this is consistent, and it has infinitely many solutions. So if you were to solve a system like this without graphing, maybe algebraically, you would get something like this. That's always true. So you weren't able to solve for x, like over here, option 1, you're going to be able to solve for x. You could say something like x is some number, y is some number. But over here, you wouldn't be able to solve for x and y. Instead, you would just get something that's always true. And that's how you know that it's going to be infinitely many solutions, because no matter what you pick for x, no matter what you pick for y, this is always true. So let's go ahead and try an example. We're going to graph this system of equations, and we're going to find the solution that way. So we have two equations, and what we can do for each of them is solve for y. And the reason for this is because slope-intercept form allows us to graph really quickly. Reminder, real quick, slope-intercept form looks like this. And if it's in this form, we can tell really fast that this is the y-intercept and that this is the slope. And so we just want to solve each equation for y. And so in the first one, just subtract 3x from both sides. And you would get negative y equals negative 3x plus 5. And then if you divide by negative 1, this is your new version of equation 1. Equation 2, just subtract x from both sides, and you would get 2y equals negative x minus 3. And then divide both sides by 2, and then you're going to get that that's y equals negative 1/2 x minus 3/2. So that's your new version of equation 2. And when we're in that form, one more time, it's really easy to tell the graph because this is the y-intercept right here on both graphs. And then the slope is this value. Okay, so we can use the y-intercept and the slope to plot those lines. Okay, so here are the graphs of our two equations. If you want to just see how we did that really quick, plot the y-intercept on the first one and rise 3 and run 1 to plot that point. And you can do it again, rise 3 and run 1 and plot those points, and that's how you can get that line. Same thing with the red one here. You can plot negative 3/2, which is negative 1.5, and then you're going to, just slope here is negative 1/2, so you're going to drop 1, which is a little weird to do because we're halfway between the tick marks, but we're going to drop 1, which is to here, and then run twice, run 2. And you can do that again, drop 1 and run 2, and so that's how you can graph that line. And so now what you're interested in is, do these lines intersect? And they do. So let's get rid of all this extra stuff here real quick. And these lines meet at a single point, and so that single point is the solution. And so we have the point where they meet, this is 1, negative 2. So the x and the y that satisfy this system of equations is 1, negative 2. And so what I would recommend is to check. If you ever are using graphing, so graphing is always an option if you want to solve your systems that way. I would recommend checking because this is based on how well we drew our equations and how well we could tell what this intersecting point was. So this is all you have to do to check. You take your equations and you plug in your point and you just ask yourself, is this going to work for both equations? So equation 1, equation 2, let's just fill in where there was an x and a y and make sure that that was correct. Okay, so our point that we think from our graph was 1 for x and negative 2 for y. And let's see if this is true. So the first one, we get 3 plus 2. Oh yeah, that one's fine, that's 5. And the second one, that's going to be 1 minus 4, which is negative 3. So yes, so that just verifies that this is in fact the solution to that system of equations. So now what we're going to do is we're going to solve a system of linear equations by substitution. So this is a nice method because we can use this one anytime, and it's one that we can actually use when we go to systems that have more equations in them. And so linear equations, again, just when we graph them, they would be lines, but let's solve it using substitution. So what you do for this method, step one, is you pick one of the equations and you solve for one of the variables. This is a choice, so you have to make a choice for step one and just pick whatever is easiest. And so if you take a look at our two equations and you have to solve for one of the variables, the least amount of work would be if we pick equation 1 and solve for y. The reason is because y is almost by itself. It's almost just a single 1y. We just have to subtract 3x from both sides. So that's our choice, but we could have picked any equation in any variable. So we just solve equation 1 for y by subtracting 3x from both sides. Alright, so that's still equation 1, but it just looks a little different. Once we have that, then step 2 is to substitute that result into the remaining equation. And so we know that from equation 1, y equals negative 3x minus 9. And what we have to do is we have to plug that into equation 2. You have to plug it into the other equation. So here's equation 2. It's going to take the place of y. So right here in this spot for y, we're going to erase y and put what it equals. And what it equals is in terms of x. So that's sort of a check at this step that we're on the right track, because when we plugged in what y is, it no longer has a y in it, it has x's, which lets us know that we're on the right track because now we can solve for x. So because we only have one variable in the result, we can solve for that variable. If we didn't have just one variable, we would just repeat steps 1 and 2, which we'll do later in a different example. And so we had just one variable, we're just distributing and then combining like terms and then solving for x. So add 27 to both sides and then divide by negative 11. So x is negative 4. And so we're almost done. We needed x and then we need y, and then that's the answer. So now that we have one of our variables, you find the remaining variable. Okay, so we know from equation 1 that the original looked like this, or we can use our modified one that we solved for y, and we just need to plug in what x equals into either version of this equation. And when we plug in negative 4 for x, we can solve for y, and we'll get that y equals 3. And so we found our solution. The x and y that satisfy our system are negative 4 for x and 3 for y. And then it's always a good idea to check, and that's one of the nice things about math, is that we can check if our answer is correct. So we just take our values and we plug them back into equation 1 and 2, and we just say, is this really equal to what it should equal for both? So where there's an x, put negative 4, and where there's a y, put 3. Always put parentheses around them, because that way you don't mess up on any minus signs or anything like this one here. This is going to turn into positive 8. And then you check, and yes, this one did equal negative 9, this one did equal 17. So that is in fact our solution to our system. So you can write the values separate like this as the answer, or you can write them as an ordered pair, because we know that in an ordered pair, the first number is always x, and the second number is always y. Alright, so now we're going to be talking about the elimination method. So we just finished the substitution method, which is a really good, nice method to use. So we're going to use the elimination method next, and we need these rules for obtaining an equivalent system of equations using this method. So here's some things you're allowed to do. You are allowed to interchange any two equations in the system, meaning you can like swap the ones on top with the one on bottom. You can multiply or divide both sides of an equation by the same non-zero constant, and you're going to get the same equivalent equations. And we'll go through an example so you'll see what all this means. You're also allowed to replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. Okay, it sounds pretty wordy, but let's see. It'll make sense as soon as we do an example. So we're going to solve this system of equations using elimination this time. All right, here's what you do. You eliminate a variable. So step 1, what we're going to do is we're going to multiply both sides of either one or both equations by some number, can't be 0, so that the coefficients on one of the variables are the opposites, additive inverses. Okay, what does that mean? That means that if we can change the way these equations look so that one of the variables has, like, let's say a positive 5 in the front and another one has the negative 5 in the front, those are opposites because we're going to eliminate the x's that way. Same thing with the y's. If this one has a 2 in the front, we can say that this one would have a negative 2 in front, and those would be additive inverses or opposites. So we're going to choose to eliminate y. So this is a choice. So you have to choose what you're going to do. You're going to say, okay, I'm going to eliminate y because, so that's what we're focusing on. Eliminate y. So this y from equation 1 has a positive 2 as a coefficient. So if our y in our second equation can have a negative 2, then we can eliminate the y's by adding the equations. So we're going to choose to multiply the second equation by 2. So we're timesing this whole second equation by 2. Every part of this equation is going to get multiplied by 2. And so we're distributing that. And then this is our new version of equation 2. So that's what we were saying on the previous slide. This is still equivalent. This is still equivalent to the original equation. This one here and this one here are the same. If we simplify, they just look different. And so the whole reason for that is because now you can add the equations. You can just put like a plus sign in between and add these equations, and you're going to get rid of one of your variables. And that's why it's called the elimination method. So you're going to eliminate one of your variables. And so for us, we're going to be eliminating y, because when you add 2y minus 2y, you get 0, 0y. So we don't even need to write that. And we have 5x plus 2x equals 7x from here. And then bring down your equal sign. And then negative 5 plus 12 is 7. And then look at that nice equation. You can just solve for x really quickly. We're almost done. We've already found one of our variables. And so we decided, we made the choice to eliminate y. So that's why we got the second equation to have a negative 2 in the front, so that when we add, this becomes 0. Then step 3, we need to substitute what we got so that we can find the other variable. Okay, so we know that x is 1. Plug it into either of the equations. We'll just plug into equation 1, and right where there's an x, put a 1, and then solve for y. Okay, subtract 5 from both sides, divide by 2, and y is negative 5. And we're done. So we found x and y using the elimination method. And if you check, you would find out that they were in fact correct solutions, and so this is the solution to our system. All right, so let's just go back to this slide real fast and make sure that you understand your options. When you're solving a system of equations using the elimination method, so that's the method, elimination method, you can change the way your equations look by doing these things. So you can multiply, this is what we did in our example, you can multiply or divide, as long as you do it to the whole equation, by any number, as long as it's not 0. And the goal is so that your variables, like let's say we had something like this, that when you add the equations, that one of your variables eliminates. Or maybe we had something like this, then this would be the opposite, so that when we add, we get rid of one of the variables. Okay, so then also you can multiply both equations if you need to. So let's take a look at this example again from the beginning, where we had a movie theater selling tickets at $8 each, and then senior discount tickets were $1 less than that, so $7. Now we have a little bit more information. One evening, the theater sold 521 tickets, and the revenue was still the $4,000. So the question is, how many of each type of ticket was sold? So we're going to use this equation we got earlier at the beginning of the video, where x represents the number of $8 tickets, y is the number of $7 tickets. And so that was our first equation. 8x plus 7y equals 4,000. But now we have a second equation, and this comes from just knowing this part right here. So each amount of tickets, however many $8 tickets was sold, is x, plus however many $7 tickets is y, so that totaled 521 tickets. So that's our second equation. And now we have a system of equations in two variables, meaning we can actually solve the system for the two variables. Okay, so we're going to use the elimination method. And if you notice, if we go back, the original equations here, we had a choice. We can eliminate x or y. We're going to go ahead and just eliminate y, and this has a positive 7 coefficient on y in one of our equations. So we need this coefficient on the second equation for y. That needs to be a negative 7. So we're going to go ahead and multiply that second equation by negative 7. And so this is just our equation 2 looking a little different. And now notice these coefficients are additive inverses or opposites. So we're going to add the two equations. And then notice that our variable did eliminate. Our y variable is gone. This adds up to 0. And so we have 8x minus 7x. So 1x equals, bring down your equal sign, 4,000 minus 3647. So x equals 353. So that we're almost done. So we know x is 353, and then if we plug that into one of our equations, we can plug that into the second one and solve for y. So y is 168. So we know that 353 $8 or non-discounted tickets were sold, and 168 discounted or senior tickets were sold. So we solved our system of equations. Let's go ahead and do this example. And so we're going to find out at the end of this example that this is an inconsistent system. But when you first see the system, you don't know that. So let's solve it as if we didn't know, and we'll see at the end why it's inconsistent. So let's go ahead and use the substitution method for this one. And we're going to solve equation 1 for y, because that's going to be the easiest variable to solve for. Notice y is almost by itself if we just subtract 7x from both sides. And so that's our new version of equation 1. And so we're going to substitute that into equation 2. And so right where there is a y, we're going to replace that with what we solved for. So this was from equation 1. And then notice you have an equation of only x's, so that's good. That means we can solve. So we distribute and we start to solve for x. And look what happens. 14x minus 14x, this adds up to 0. And we get 8 equals 1. So at this moment, notice we were trying to solve for x. The goal was, what is x right here when we substituted? And x went away. And we got something false. This is never true. So we got a statement that's never true, and we weren't able to solve for our variable. And so when that happens, that means that the system is inconsistent and has no solution. So we solved it like we would normally, but at this moment when we got rid of our variable and we got a false statement, then that's when we conclude the system has no solution. So this is actually the answer. No solution is the answer to the system. All right, let's go ahead and do one more. This time the system is going to be dependent equations. Again, you're not going to know this ahead of time. I'm telling you now that they're dependent, but you would solve it normally, and then you'll conclude at the end that you have dependent equations. So let's take a look. We're going to go ahead and use the elimination method this time. And if you notice what you have, you can multiply the to get rid of the x's or the y's. It looks like the easiest choice is going to be to get rid of the y's, because if we multiply the first equation by 3, then this would be a negative 3 here, and they'll add up and eliminate the y's. And so let's just do that real quick. And so we have 3 times the first equation, and when you simplify, look what happens. 12x minus 3y equals 18. When we add the two equations, everything gets eliminated. 12x minus 12x is 0, minus 3y plus 3y is 0, and bring down our equal sign. 18 minus 18 is 0. So everything got eliminated, even though we were just trying to eliminate one variable. And so this one here, the statement 0 equals 0 is true. So that was a true statement all the time. This is always true. It's not a false statement. But we weren't able to solve for y or x. We were trying to solve for a variable, again, either variable, and they all got eliminated. But what happened was a true statement was the result, and so that means every x and y will always work no matter what we plug into our equations for that system. And so if you want to check, you could just pick a few values for x and y, plug them into your system, and you'll figure out that they're going to work. So it's because these two equations, when you simplify them, they actually ended up being the same equation. And so what you can do for an answer like this, you can say y equals 4x minus 6, where x can be any real number, or you could solve for x and say x equals 1/4 y plus 3/2, where y can be any real number. And these are both the same solution. And you wanted to say, instead of infinitely many solutions, you do want to give it a little bit more context. So that's why you solve the equations, either for y or for x. And then just mention that the variable can be any value. So in set builder notation, we can say the set of all x's and y's such that these equations are true, where either x or y is any real number. Okay, so that's the answer. And I just want to show you, going back to the original, where we figured out that x and y could be any real numbers to satisfy the system. And so where we got our final answers from was, if you notice, this is actually the same equation as the first one if you just divide everything by 3. So if we divide everything here actually by -3, then we'll get 4x, -y, and 6. And so they're the same equation, and then we just solve this equation for x or for y, and that's where that final answer came from. Alright, so that's it for this one. In the next video, we're going to talk about systems of 3 equations. See you soon!